and let the recording begin. So then we will take this one. So in our last class, we have been talking about the constraint motion, and we considered few few examples to show you how the constancy of the string length, this theorem can be applied to find out the the constraint motion of multiple bodies. So this was the concept that we need to consider the maximum, the entire length of the string, and then we see that this entire length of the string we need to consider there, and we see that this constancy of the string length has been used to find out the relation between the motion of these two masses. Today we will take up an example problem, how to apply this principle here. For example, bolo.
এই যে একটা প্রবলেম বলেছিলাম না স্যার হোয়াটসঅ্যাপ, ওটা পরে বলবো তাহলে স্যার?
হ্যাঁ, এখন নয়।
আচ্ছা ঠিক আছে।
হ্যাঁ, এখন নয়, ক্লাসের পরে সেগুলো সব, বা অন্য দিন, যদি আজকে না হয় তাহলে অন্য দিন। So we see that here, this is the consideration. Suppose this is the problem from again the Merriam and Craig. The problem is from 2/208. Here we are being given these two masses. For example, at a certain instant, we see this is the system. It's a system of complex pulleys. There are several pulleys which are connected, and they are connected by means of the strings, and we see that this string is there, and we note that this is the thing. We have the block A connected by means of the strings here, and then we have another block B. So there are two blocks here. Now at a certain instant, the velocity of the cylinder B, that means this cylinder, is moving down with a speed of 1.2 meter per second. So let me see here. This is the velocity. We can consider that this is the the velocity of the block B that has been shown here in the downward direction. That is 1.2 meter per second. This is your velocity VB. We can write this is 1.2 meters per second, and we have the acceleration vector, and the acceleration vector here is is being given in the upward direction, which is AB, that is being specified as 2 meter per second square. So once these data are being given to us, we have to find out basically the the what is called as the velocity and acceleration of block A. So we need to find out the velocity and acceleration of the block A when these things are being given to us. So in order to solve this problem, once again we will apply the principle of constancy of the string length, and then I will show you the another method by which we can solve this problem, which is called the physical method of the solution. So in this case, first we see that we first of all fix up our reference plane. Since this pulley is fixed, so I can consider the line drawn through it. Say, let us consider this line which is being drawn through it, and we say that this pulley is it's very small. We ignore the size of this block, and since this pulley is rigidly connected with this block, it shows therefore whatever is the velocity of the block or acceleration, that will be also the case with the center of this pulley. This pulley, its center, so velocity of block A and acceleration of block A is basically the velocity and acceleration of this point. So we can therefore consider this is your the length of the this is the coordinate dimension we say this is the position of, this position of this pulley A. So we say this pulley is dimension, this distance we call it as XA. So this is being fixed. We consider this length is fixed one. Now you come to this one. We note from here that if I say this is also fixed here, so I can consider that this length, right, this is also going to be constant because the distance between these two fixed points. So we can call this distance as A. So constant, we call this distance as A. Then we see from here to here, this distance, I mean to say the center, here we see that this distance is also constant. So we call this distance as B. And we suppose that this is the, the reference of measurement of this one, of this system. And we note from here that the center of this pulley. So let's say this distance, let's say, because the velocity of block B is also equal to the velocity of the center point. So we term this distance as, we call this distance as XB. We call this distance as XB. So this is XB. So let's say these are our dimensions by which we are now in a position to write our constraint equations. So if I suppose that this is the consideration, let us now note that how much is the total length of the string here. This is the one string is just a single string system is going like this, moving around entire system. So first see here, and we will neglect the portion of the string which will be wrapped around the pulley, correct? Because we know that portion is constant and these pulley dimensions are very, very small. So we are not taking into account the string portion which is wrapped around the surface of the pulley. So here we see that this total length of the string in this case is going to be twice XA. Then we have this constant length of the string, we call this as A plus A. Then we see this is the string, so one string length is XB, so we add XB here. Then we have two strings and we will neglect this slight obliquity of the strings. Unless mentioned otherwise, this obliquity of the string needs to be ignored. So we will assume that this string is as good as
Sir, why it is 2 into XA?
Why it is 2 into XA? So because you see this side there are two string systems here. So one is this XA portion and another is this portion. So that is why it is 2XA. বুঝেছো?
Okay, sir.
That's
it.
So we have this is A, and then we have this portion of the string. I am saying this is XB, and then I neglect the small portion of the string which is wrapped around the surface of the pulley. Then we are considering this length of the string and we will neglect the obliquity of this string. So it means that we will neglect the slight obliquity of the string and we take them as good as parallel to it. So we say that this string is actually parallel to this one and this one. So I find therefore that this the length of the string then becomes equal to what? We see here this is XB and then we have this portion and we can say two such portions are there. So we can write this will be plus 2 into this is XB minus B. So this is XB minus B and this entire length is going to be constant. Okay. So I can say from here that this is, if you can simplify the constraint relationship, we can say therefore how many 2XA is there? So 2XA and then we have 2xb plus xb, so it is plus 3xb, correct? And the result becomes equal to, and all these a minus 2b constants, so all these things are constants, so we can take this to be equal to constant. So we find that my the constraint equation here, this is my constraint equation that I am getting. So at any point of time, the position coordinates of the the individual blocks are being given by these dimensions, and this is the relationship. So we use this relationship because this xa and xb all, they are functions of time, because as time changes, the distance between this center and this block will change. Similarly, the distance between the center of this floating pulley, this is a floating pulley, it will change, and as a result we find that this will be the case. So these are all functions of time. So since these are all functions of time, we can differentiate them with respect to time and get the desired relationship. So what is the desired relationship then? So differentiating it once with respect to time, we get this is twice x dot a plus it is going to be 3x dot b, and that is going to be equal to 0. So that means therefore that again, if we differentiate it with respect to time, then we will be getting twice x double dot a plus 3 times x double dot b, they are going to be equal to 0. So from this equation 1, and we call this equation 2, so from this equation 1 we can say that VA, so from 1 we can write, from 1 we can say VA is equal to, we are going to write it equal to minus 3 by 2 into VB, correct? Now, now I see that VB is being downward, it's being given 1.2 meter per second, and our position coordinate sense is also downward. So it means for us VB equal to plus 1.2 meter per second. So we can therefore say that it is minus 3 by 2 into plus 1.2, plus because we see that this sense and the sense of the coordinate to locate this position, they are same. So therefore the result becomes equal to how much? It is becoming minus 1.8 meter per second. So VA turns out to be minus, which means that the velocity of the block A will be in opposition with the displacement direction, position vector direction of block A. So you see the position vector here is down the inclined plane. So as a result, we can say that the actual direction or the sense of the velocity of block A will be therefore in the upward direction, and the magnitude of this, so we can say therefore we will report the answer like this. We can say VA is equal to 1.8 meter per second and its direction is up the inclined plane. So this is how you need to report your answer here, because these are, find the corresponding velocity, velocity being a vector quantity, so you need to specify its magnitude as well as its sense, and this will be given in this manner. Now again, if I take from equation 2, so if I say this we have used from equation 1, then we are using, say, from equation 2 if you go, so then what we see from here, from 2 we can write that acceleration of block A is going to be minus 3 by 2 times acceleration of block B. Now here acceleration of block B is being given in the upward direction, so it is in opposition with xb. So for us acceleration of B is a negative quantity, so I can therefore say it is minus 3 by 2 into, we can write this is minus 2, and therefore the result turns out to be 3 meter per second square. and it is turning out to be plus. So that means that we need to report our answer in the way that acceleration of block A is going to be 3 meter per second square, and it should be down the inclined plane because the XA is down the plane. So we have, this is our acceleration of block A. So therefore this will be therefore my answers for this problem, where we see that we need to find out the velocity and acceleration in this way. So you see, this is a simple method by which we take into account the constancy of the string length consideration, and you need to specify your coordinates in such a manner that you will be going to do in this way. So this is our, we can call it as method 1. That means the method about which we have discussed in our previous class. So we can call this as our method 1. Now we have the second method, and in the second method, this is called the physics of motion. Second method, it's called physics of motion. The second method is, now which method you will be going to apply in your problem, of course that depends upon your convenience. Some problems are more conveniently solved by method 1. So in this case we identify, now there are certain the pulley systems are here. So I just show you, these are your pulley systems. Now your pulley systems can be, this is one category, correct, where your pulley is fixed and the strings are, either the strings are connected vertically down or the strings are connected vertically up. So this is one system of pulley, we call it as a fixed pulley. Fixed in the sense that the center of the pulley is connected to the fixed ground. So it means that this pulley is going to rotate either in the clockwise direction or in the anti-clockwise direction. Suppose this pulley rotates in the clockwise direction, then this will be the corresponding vector diagram for the velocity and acceleration of the pulley. So this is therefore the velocity vectors will be, since this pulley is rotating about the center, so the velocity and acceleration must be tangential and perpendicular to the radius that I can draw here. So this will be therefore this side, suppose the string is connected in the upward direction, the strings are connected upward. So in that case we will find that this end of the string is suppose going in the upward direction, or this end of the string is going in the, and it is going in the downward direction. Both these magnitudes are equal and opposite because your pulley is rotating about the center. So if I call the angular velocity of this pulley as omega, then this velocity is omega into r, this is also omega into r. It is, of course, this vector diagram is independent whether your strings are connected vertically up or they are connected vertically down. It does not matter. So only thing matters is the sense of rotation of this fixed pulley. So if the sense is not known to us, then we have to fix it up by considering the other physical situations. So therefore this will be one kind of vector diagram when our pulley is rotating in the clockwise direction. If the pulley rotates in the anti-clockwise direction, the corresponding vector diagram will be like this. So either these black arrows represent the velocity or they represent the acceleration of the strings which are connected to this pulley at these 2 points. So this can be one category which I call as a fixed pulley. Now there can be another category, the pulley can be connected in this manner. You see, this end of the string is connected to this fixed ceiling. So what it means? It means that the point of the string which is in contact with the pulley here, it is going to be having 0 velocity because the strings are inextensible. So it means that all the points on the string must be having the same velocity or must be having the same acceleration. So as a result, since all these points this string is rigidly connected to the ceiling, so it means that all the points on the string are at rest, and therefore this pulley, this point is actually, is in at condition of rest. So your pulley will rotate about this point. This will be your center of rotation of the pulley. So therefore, again, the rotation sense can be either clockwise or it can be anti-clockwise. If the sense of rotation of this pulley is in the clockwise direction, this will be the corresponding vector diagram. Because all are rotating about this point, so it means that this will be your linear velocity diagram, omega into r or alpha into r. So it means that with radius, the velocity and acceleration varying linearly. So this is the linear variation which I can show. So obviously we find that the center of the pulley is not fixed, unlike this one. Here the center of pulley is fixed, but in this case the center of the pulley is not fixed. So if I know the extreme end velocity here, so if I know that extreme end velocity here, then I can find out the center velocity, which will be half of this extreme velocity. Similarly, if this is the the extreme end acceleration of the pulley, then the center acceleration will be just half of it. So we find therefore, this is how your velocity or acceleration diagram of the pulley will be. So this is the case when your pulley is trying to rotate. That means this pulley is trying to rotate about this point in the what is called in the clockwise direction. The exactly opposite velocity acceleration diagram will be if your pulley starts rotating about this point in the anti-clockwise direction. So this will be therefore the sense. So this pulley is going to be rotating is with respect to this point, because this point is fixed point. So whenever you have this pulley, you need to find out, search for this, the point of zero velocity, correct, or point of zero acceleration. That is called as the instantaneous velocity center. So the pulley will actually rotate with respect to that point instantaneously. For example, here it is always, this is always being fixed. So this pulley will always freely rotate. So it will undergo free rotation. But here, this is actually the combination of rotation and translation. It is because that the center line of this center point of the pulley is having the motion. So it means the translational motion of the pulley about the center of mass will be given by this vector or this vector, and we can think that the entire pulley is rotating with respect to the center. So then ultimately the total motion of this pulley, as it is shown here, this can be considered, because anyway we can consider it to be rotating with respect to this point and this point, but actually this motion can be thought of as a combination of translation and rotation about the center of mass of the pulley. So this is how we can do it, but we do not have to think of that combination motion. Just see, locate the instantaneous center of rotation and accordingly draw your vector. Thirdly, we have the case where neither, here at least one point on the string on the pulley is fixed, but you can have the consideration of a floating pulley. This I call it as a floating pulley, where neither string is fixed. So in that case, your velocity diagram or acceleration diagram will be little bit involved. Either the velocity diagram or the acceleration diagram will be like this, or it will be like this. This line can go, in this case, you see, this line can go towards the left hand side of the center, or it can go towards the right hand side of the center. What will be exact nature of this will of course depend upon the magnitude of this vector and magnitude of this vector, because these two magnitudes will actually define where will be this line, going to cut the horizontal radius of the pulley. So the point at which this, this line is cutting this horizontal radius, or that means this point or this point will be referred to as the instantaneous center of rotation of this pulley. That means this pulley can be here. Say for example, this pulley can be considered to be rotating with respect to this point, and in this case this pulley will be considered to be rotating with respect to this point. So with this, three possibilities, we can actually solve any problem in the strings. For example, if I come back to our present problem here, which we have already solved, we can apply this principle to solve it. Only thing we need to identify, the pulley proper. For example, you see this pulley, if you look at this pulley here, we note that this pulley, the string of this is connected to the center here. So this is where the string is connected. So it means all points on the strings are going to be fixed. So this pulley will try to rotate with respect to this point. Correct? So either the rotation will be in the clockwise direction, or it will be anti-clockwise direction. That will define the sense of the motion of this block A. Coming to this pulley, you see the center is fixed. So this pulley is purely rotating. So this is our case 2, which we have shown here. So the first pulley belongs to this category, and the second pulley belongs to the first category. I mean to say, it belongs to this category. It belongs to this category. So we note that therefore the corresponding velocity diagrams can be very easily drawn here. Now coming here, you see this pulley. We again note that the center of the pulley is fixed to this fixed plane. So it means that this pulley is also rotating freely with respect to this point. So it is undergoing pure rotation. Again, this pulley therefore belongs to category 1 of our system, as also this one, because this is also fixed. So this and this will belong to category 1. But see this pulley. In this case, we note that here, we note that this pulley, is not actually, we see that this is a floating one, because neither of these strings are, fixed direction. So how to solve this problem? How to solve this problem in this case by method 2? So let us assume, because suppose we do not know anything about the senses of rotation. So let us try to see how we can, we can draw the figures of this. Suppose if I consider this, start with the first pulley. So let us take the first pulley here and start drawing its diagram. So this is the first pulley that we are going to get. Say this is our first pulley that we are going, this is our first pulley that we are going to draw it here. Say this is your first pulley. Now since this point is fixed, we have seen that this point is going to be fixed. So either this pulley will rotate in the clockwise direction, or it is going to be rotating in the anti-clockwise direction. So which direction to start with, I do not know, but here at least the velocity of this is being given in the downward sense. So in the hindsight of my mind, I can therefore say, okay, I just take as a trial to see that since this is going downward, I have a hunch sense that this pulley, this block might go in the upward direction. So let us see therefore this pulley is going to rotate in the clockwise sense. So if I therefore consider, or you can start with, you can draw in the anti-clockwise sense also. I will ask you to check the figure at your home and come to the required conclusion that if this pulley starts rotating in the anti-clockwise direction, how you are going to match it with this direction, and then you need to rectify the sense of rotation of this pulley. So I therefore see that tentatively we assume this pulley is rotating in the clockwise direction. So therefore this will be your velocity diagram. So you can see this end is fixed. So we see this will be the velocity of the one end. Actually it is not going through the center, sorry. So this line, this will be half. So this motion will be half. That means the motion of this center block will be half. So whatever is this vector, so if I call this vector, if I call this as velocity of A, because the center motion of this pulley is actually the velocity of block A. So if I call this is velocity of block A, then the velocity at the upper end is going to be 2va. So this string is moving in the direction 2va. So it means that this pulley, this string, so if I just show it with the red arrow, so it is going in this direction tentatively, it is going in this direction. So it means that this pulley is also rotating, so this string will also go in this direction because this is a fixed pulley. So in this case, if this one goes in this direction, this pulley will try to rotate in the clockwise sense. As a result, the motion of the string will be like this. So coming to this one, this pulley, I see that this pulley will also then rotate in the clockwise sense. So if the string is like that, then this string is going in the downward direction. So this string is therefore going in the downward direction. And we note that if this is going in the downward direction, now I do not know the sense of rotation of this pulley. It might go in this direction or it might go in this direction, but it is being given that the center of this pulley is moving in the downward direction. So since the center of this move, because the velocity is being given in the downward direction. So if I come to draw the floating pulley here, if I come to draw this floating pulley here, so we find this is our floating pulley, and we just see that this end of the string is actually going in the downward direction. Sorry, this end of the string is going in the downward direction. So let's see this end, we call it as this one. How much is this? Because we have seen this is 2va, so it means this is 2va, this is 2va, and also this is 2va. So this is 2va. This velocity is going to be 2va. And the center of this, the center line of this pulley, it's in the downward direction. It is in the downward direction, and we note that the center, since it is in the downward direction, so just we can see that this center is going to be in the downward direction with this, which means that the string which is attached here is also actually going in the downward direction. So I can say this string is going in the downward direction. So it means that this string is going in the upward direction. Now since your pulley is rotating here, it means this side, it is rotating here like this. So it means that this, the upward vector, this upward vector should be in opposition with this vector, and they should be equal to each other. So I can therefore draw the remaining triangle, which will be equal to this. So it will be equal to this. So I draw this triangle, and thus I join this to complete this triangle here. So we find from here that this will be thus the vector diagram for this floating pulley. So we find therefore that the vector diagram of this one is going to be in like this. So it means that this velocity and this velocity must be equal. So it means since this pulley is going down with a direction of 1.2 meters per second, so this must be also 1.2 meter per second. So if this is 1.2, then this is also 1.2. So therefore it means that this line, green line, is actually bifurcating this radius. So if you see, this radius line is being bisected by this point, because this vector and this vector basically are equal. So if I call the radius of the pulley as r, if I call this radius of the pulley as r, then this must be equal to r by 2, correct? So if this is r by 2 and this is r, then by the similar triangle, I can see that the length of this one, I need to say 2va divided by your a velocity called 1.2, 2va by 1.2, we find that this should be equal to, this total distance, how much it is? It is r by 2 plus r, so it means it is 3r by 2, so it is 3r by 2 divided by this distance, which is r by 2. So it means that the velocity ratio here becomes equal to 3. So it means therefore that the velocity of block A is going to be equal to 1.2 times 3 upon 2. So it means that the velocity becomes 1.8 meter per second, and that velocity should be, we can match the diagram ultimately here by assuming that this is the your sense of rotation, this being your sense of rotation. By assuming we can match it like that, so we can match it in this way. So we see that the corresponding velocity for the block A, that we have assumed that this pulley is rotating initially in the clockwise direction, is correct, because we are trying to get this velocity and we can completely can determine the thing. Now the question can be that how do you understand that this pulley is this rotating in the clockwise sense? What happens if with this given condition, if I assume this pulley is rotating in the anti-clockwise direction? So in that case, you see everything here will be opposite. So you see that if I assume that this pulley rotates in the anti-clockwise sense, it means then this vector will be in the downward direction. So we can draw the vectors. This vector will be downward direction, this one will be in the downward direction, this one will be in the upward direction, with this point going in the downward direction. So if you try to draw then the corresponding figure for this pulley, if you just see the corresponding figure for this pulley, you just note that this one is going, this one is going to be in the upward direction, because we have assumed this one is going in the upward direction, and this one is going in the downward direction. I know this sense because it is being given, that this block is having a downward velocity. So I know the vector of the center of this pulley. So it is in this direction, correct? So since I have assumed this, and I know this, I can draw the line through it. And if I draw the line through it here like that, if I properly try to draw properly the line, it's very difficult and control the straight line in tab. Okay. So if this is going to be the line, then you see that this motion, this velocity is going to be in the downward direction. But this is not possible. Why? Because we just see that, and also I find that the two velocities are different. That means the center here and the velocity that I will be getting, if I assume the other end is moving in this way, they are not equal. But then it is not possible. Why? Because just now we have seen, since this string is connected with this fixed pulley, so it means that the two ends velocity must be equal. So in other words, what it demands is that an equal and opposite, not only they are equal in magnitude, but they are opposite in direction. But it contradicts here, because here we find they are in the same direction. The directions are not opposite, number one. Number two, their magnitudes are also not equal. So it is not physically satisfying the requirement that this string is passing over this fixed pulley. So it shows therefore the assumption that we started by assuming that this pulley, by assumption that we started that this pulley is going in the anti-clockwise direction, rotate in the anti-clockwise direction, is absolutely not possible. So therefore the only alternative left with me is the case when your pulley is rotating in the clockwise sense. So it is not that you have to guess the proper sense of rotation. For example, here we have guessed that if this one going down, then this one might go up. So that was our guess. and depending upon that guess, we started drawing the diagram from this end till we come and match the diagram, and we find that we have a perfect match here. But even if I am not able to guess my sense of rotation of this pulley properly, I can start with the improper guess the way I have shown here. That means I just consider that this pulley is rotating in the anti-clockwise sense, and my velocity diagram, it looks like this. So with this we started our analysis, and with that we started our analysis, and we come to a impossible solution. This can be a very possible solution, but in this particular perspective it is not possible because of the fact that these two strings are connected to a fixed pulley here, and therefore the requirement is that these two vectors must be equal in magnitude and opposite in direction. So as a result, to match this physical the constraint, I cannot have the rotation of this pulley in the anti-clockwise sense. So if it is to rotate at all, then it must rotate in the clockwise direction. So this is how, therefore, we can, even if we can start with a faulty, the sense of motion, we will come to an inconclusive end, and that will, direct us that, okay, to start with, whatever you have assumed is not correct. So the obvious alternative will be that this pulley will be rotating in the clockwise sense, and the string will be going like this. So the vector, green vector, which I have shown here in the top here up to this, we see that this is actually not tenable. So I just erase this, this sense here. I just take out this sense and retain the senses here like this, and we find this is the proper way of, finding out the answer. So once this is being done, now you can assume that, okay, when I see that this one is going down, I see that this will be the proper vector orientation. So obviously for acceleration, it is obvious that if this one goes up, that means this center is having the upward motion. So essentially it means that all these vectors will get reverted, and ultimately for acceleration, of course, this pulley, will be taking to be rotating in the anti-clockwise sense, and therefore by proper diagram or the velocity diagram here, that means the diagram over here, we can draw and finish our analysis. So we can therefore say that with this vector diagrams we will be able to solve the acceleration as well. So I will ask you to solve this problem, finding out the acceleration, by method 2, drawing the proper diagrams, and convince yourselves that this will be the proper senses, and we can be able to find out the acceleration of block A from there. So acceleration analysis I am not doing. I am leaving this to you as a homework in order to complete your analysis. Okay. So once this is being done for us, okay, thank you. Now once therefore, so I therefore see that, this, you need to remember, this you need to remember, these are only the three possibilities, correct? Your possibilities can be like this, only thing that the center line can be shifted left or right. This is the floating pulley, this is where you have to apply your engineering sense or apply your sense of mechanics to identify what will be the proper senses of rotation. For example, this present problem, how I solve it, I show you. I just show you that how I will be going to solve this problem in this case. Now, coming back, coming back to this, if I see the second problem, let's take the second problem. Again, I am telling you, before going into the second problem, whether you will be going to solve by method 1 or method 2, that will depend upon your convenience. The advantage of method 2 is that here you can be able to understand bit by bit the physics of motion. You will be able to feel in which way your things are moving. And method 1, the advantage is it's sometimes is very simple, as for example in this case it is just a one-liner, but the disadvantage is that here you are not getting the senses physically. Correct. So at the end only you are getting the senses physically, but method 1, 2 will show in every step the kinematics of all the pulleys that are involved. Here in the method 1, the kinematics of the pulleys that are involved here is completely absent. We are just doing it mathematically, closing our eyes, we are doing this thing mechanically. But this is actually the engineering comes in method 2, where the senses you need to understand the kinematics of them. Okay, so therefore with this comment, now I come to the discuss this second type of problem, and this is second problem. It's again from the book of Merriam and Craig. I am taking this book as my textbook because this is freely available. So I take the problem from here and consider the thing, and I will urge you to solve the problems from the respective chapters which I am discussing. Please don't try to jump and solve the problems from the chapters which I have not covered so far. Please do not do it, then it will actually hamper your development or understanding or the concept of the solution, as well as it will be an inconvenient thing for me because I have not explained the topic to you and you are asking me to solve the problem on that topic. Please don't do that. Go with me, solve the problems on the chapters which I am actually covering so far. So now I come to this problem number 2 by 24, which shows that this is system being given to us. So this is a system. Physically understand the system. There is a plunger here, oil cylinder, and this is the plunger, and the plunger is carrying a small pulley here. Okay, this is a small pulley. The string is connected this way, and ultimately this string is connected to the block B, which is fixed in the vertical slot. So it means that this pulley is constrained to move in the horizontal line, and this end of the string is constrained to move in the vertical line. So that is the being the problem being given. So this is again a dependent kind of motion, and the key method or key step, the key step is actually to identify the constraint. Just to identify what is your constraint and try to explain your constraint conditions mathematically. So constraint you need to identify and express it mathematically. For example, if we see here, the rod of the fixed hydraulic cylinder is moving to the left with a constant speed. So it is being given, this is the rod of the hydraulic cylinder. It is constrained to move with a constant speed, VA, that is 25 millimeter per second towards left. Determine the corresponding velocity of the slider B. So this is the slider B. We have to find out the velocity of the slider B when SA, that means this distance, is being given to be as 425 millimeter, where it is being given the length of the cord is 1050 millimeter. That means this length, this side length plus this side length, and also the portion of the string which is being wrapped around the pulley surface. This total is taken to be 1050 millimeter, but a cautionary sentence is being given to you, and the effects of the radius of the small pulley may be neglected. That means the pulley is here very small, so we can consider therefore the string length is essentially from here to here plus here to here. Okay, that means the portion of the string which is being wrapped around the pulley surface, we have to neglect that small portion of the string. So total length is taken to be as, so we can write it like this, that we are being given that AC plus BC, we can take this to be equal to, so A being the center of the pulley, and all these will be measured with respect to the center. This is being given to be 1050 millimeter. I express it in meter, so I say this is 1.05 meter. So it is being given. On the other hand, you see from here, you see this AC distance is being given to us. This distance is 250 millimeter, and at the instant we have to study the velocity when at that instant the SA is 425 millimeter. But please remember, this is not constant. So the thing that is being given, SA equal to 425 millimeter, is the instantaneous figure. So I can therefore say when SA is being given to be equal to 0.425 meter, correct? We can find out the value of AC. And what will be the value of AC? Now that is equal to square root of 0.425 square plus it is 0.25 square. Why 0.25? Because this dimension is being given as 250 millimeter. So I just apply the Pythagorean rule and I find that this will be the distance of AC. So how much will it be? So if you take the calculator and just calculate it, 0.425 square plus we have 0.25 square, the result becomes equal to this one. So I can take the square root of it.
0.493.
0.493, correct. So this distance, we therefore take this to be equal to 0.493 meter, correct. You should also do the calculation with me. As I told you, a cautionary statutory warning that I made quite often mistakes while doing the board work in haste. So this is AC, that is 0.493 meter, and accordingly we can calculate the instant when AC is being given like this, the BC value, this is AC plus this is AB, not BC. See, here also I made a mistake and I am not saying anything to me. So this is AC plus AB, AC plus AB. So we can therefore say that how much will be AB? So we can just say that it will be 1.05 minus 0.493. So that will be your length of AB. So again, if you take this one, so you see, what was say? 0.556 meter. Okay, thank you. So that will be your, the length of this. So this is when, SA is being given. But we have to use the constraint not for a specific condition, but in general. So as a result, we need to consider certain things. For example, in order to find out the velocity of block B, we need to specify its coordinates. So how we can specify the coordinates? Okay, I can use this, this line, this horizontal line, it is a fixed line. Because this is, going through the center line of this fixed, fixed hydraulic cylinder. So this serves a fixed reference plane, reference line for me. And I just take the, this as your position of block B. So I call this as XB. So now I try to express my constraint condition. So what will be the constraint condition? Again, I like to see that AC plus AB equal to 1.05 meter. Now, you see all these are in general consideration. So it means from here that the length AC, so I can write this general situation something like this, that square root of SS square plus 0.25 square, correct, 0.25 square plus we can say this AB, which we can write it something like this, it is square root of SS square, okay, plus it is AC square, and that must be equal to constant. And this is, Hussein, I will talk you later. I'm in a class now.
Yes, sure.
Okay. So we see that this is constant, and this constant value is 1.05 meters. So this is your thing. This is the thing that we are getting. Now, this is the constraint relationship. That means that every time we need to satisfy this. So I can differentiate this with respect to time. So if I differentiate it with respect to time, so it will be what? We can say that it will be root over S square plus 0.25 square, correct? This should be SA into S dot A. The 2 cancels out, so I am not writing that one. Plus, now you are getting this one. This will be, root over S square plus XB square plus this will be SA into S dot A plus it will be XB into X dot B, and that must be equal to 0. That must be equal to 0. So we see therefore our equation becomes something like this, and my objective is to find out the velocity of block B. So I can write from here that XB by root over S square plus XB square, okay, into this factor into X dot B, which is nothing but VB, turns out to be minus. You see here it will be minus, and minus of what? I can take SA into S dot A common and can write that it will be 1 by root over S square plus 0.25 square, okay, then it will be plus, you see, 1 by root over S square plus XB square. So you see therefore that this is the relationship between this, and I note that it is being given that, you see, the velocity of this end, I mean to say VA is being given to be equal to how much? It is being given 25 millimeter per second towards left. So conditionally expressing this condition, that S dot A is going to be equal to minus 0.025 meter per second. Sorry, it is plus, sorry. So it is plus. Why it is plus? Because of the fact that since this velocity is towards left and you see this sense is also towards left, so it means that your velocity and the position vector, they are in the same sense. So you can therefore say that S dot A is being given to be equal to plus 0.025 meter per second. Had this been in the reverse direction, দেখো কে এখানে ঢুকতে চাইছে, ঈশান মন্ডল, আজকে আর এন্ট্রি নেই। So we see therefore that this SA, this left hand side velocity, it is positive, because this is also left hand side, this is also the left hand side. So we don't have, if this end is moving in the opposite direction, then of course we need to put a minus sign. So please be very careful regarding this thing. So if you see that your S dot A is positive, so this is going to be positive. So ultimately all other things being positive, so ultimately you can see that your VB is turning to be negative. So VB is less than 0, which means that as you move this towards left, you see this block will start moving in the upward direction. Why upward? Because this VB is coming out to a negative sign. So this sense and this sense must be opposite, and as a result, you see this negative sign will be explained. So one thing is pretty clear, that the velocity of block B, so it indicates that velocity of block B is going to be in the upward direction. So once this is sought, I can find out the magnitude of the velocity ignoring this negative sign. So what I can do is this, I can therefore say that if I just talk about the magnitude of the velocity of block B, then that should be equal to SA into VA, because S dot A is VA, and I can write that it should be divided by XB, this by divided by XB whole into, we can say this is 1 plus square root of SS square plus XB square divided by it is SS square plus 0.25 square. So that will give me the magnitude of the block A's velocity, block B's velocity, sorry. So we see therefore just substitute. Now you note that in order to find out this velocity, you see it depends upon the position vector, position variables. I mean to say in this case SA, XB, all these are position variables. So what you need to find out? Of course, you need to find out the velocity of block B when SA equal to when SA is equal to 0.425 meter, that is being given, and you see that your XB. So how much is your XB? So that XB you can find out. That XB you can find out from here. So use this relationship to solve for XB, or already we have already solved the dimension AB, and this dimension AB is nothing but square root of SS square plus XB square, correct? So since SA is known to be 0.425 meter, corresponding to that, how much will be the value of XB, we can find out. Either use this relation or use this, whatever you can feel like. So you see, from when SA is being given to be equal to 0.425 meter, in that case, what will be the value of XB? We need to find out and plug those values. So plug these values into this equation. If you now plug these values into this equation, considering VA is equal to how much? That it is 0.025 meter per second. This is your VA. This is the and insert into this equation to find out what will be the instantaneous magnitude of block B when SA equal to 0.425 meter. So you see that your velocity, so this is the equation which shows you that the velocity depends upon your position variables. Earlier, whatever constraints we have been using, if we just recollect the previous problem, in this case, if you look at this constraint relation, here you see when you differentiate it, apart from velocity, no other factor is present. That means here, when you are trying to get your x dot b or x dot a, I find that x dot a is totally function of x dot b or vice versa. Correct? That means in this case, normally we therefore find that if we have, in this case, when we are having the constraint relations, you need to remember that if I consider any object, say XA, there are two objects, XA and XB. So if I am to find out the velocity of XA, I mean to say block A, say this is x dot A, normally it is function of XA, XB and x dot B. Normally it is this case. And x double dot A, acceleration of block A, can be again some mathematical function of XA, XB, x dot B, x dot A, x dot B, and it can be also function of x double dot B. So normally these are the things. So you should not always expect that you will be having a very simple sort of relationship. Say for example, the velocity and accelerations here, they are very simple because they only depend upon the acceleration of the other. But what I am trying to say that it may not be that your velocity of one will depend upon only velocity of other. It may depend upon the positions of these two variables, like in this case, like this present problem. See here, velocity of block B, it is function of how many variables? You see, it is function of SA, that means XA, then it is function of xb, then it is function of your va. So you see, one velocity depends upon so many parameters. Similarly, this is not given, this question is not being given, but I ask you to solve this problem. Say for this problem, it is being told that other things all remaining the same. You are being told to find out the corresponding velocity and acceleration of slider B when SA equal to 425 millimeter. That means not only you have to find out the velocity of this block B, we should be able to determine the acceleration of block B also. It is being given that this end is moving with a constant velocity. What it means is that acceleration of A is going to be equal to 0 because this is constant. So it does not have therefore any acceleration. So acceleration of block A will be therefore 0. So just solve this problem at your home. First of all, finish this problem at your home to find out what should be your velocity of block B in this case. Already we have seen this velocity is moving in the, going to be in the upward direction. So the problem is sorted out. Now the second question which will be given to you as a homework, from this find out what will be the acceleration of block B. So you will be able to appreciate that the constant relations are not that easy. Sometimes they require, the what is called, they require quite a, the long and involved process of doing your sum. So I think you have understood this problem, and now I will ask you again to solve this problem, to solve the remaining problems, or the problems from up to this. So with this we are finishing the chapter of the first chapter of rectilinear kinematics. So this is the end of rectilinear kinematics. Again, my words of cautions to you is that you just devote yourself, spend your time to solve the problems from the chapters which I am teaching. I am not covering the portions of kinetics. Please do not jump to solve the portion of kinetics right now. So start solving the problems from the kinematics portion only, where there is no involvement of forces and all. Now today, you see that we will open the new, new thing, that is what is termed as the new chapter. So that new chapter is the particle kinetics. So far we have covered particle kinematics. Now we will take this from today. We will take up the particle kinetics. So as you know that kinetics deals with the causes of motion and kinematics deals with the effects of motion. So we have so far covered the particle kinematics in rectilinear and curvilinear motion. So just going in the same line, the kinetics will be divided into broadly two categories. The first one will be called rectilinear kinetics, and we always consider particle, and then we have the curvilinear kinetics, and this curvilinear kinetics, here we again have the divisions xy system, nt system, normal tangent, nt means normal tangent, nt system, nt, and then finally we have the r theta coordinate system. So this will be our the division of particle kinetics section. So you see here the basic governing equation for kinetics is of course Newton's second law of motion. So this is Newton's second law of motion. It is much studied by you, second law of motion. So much studied by you. In this case, what we will be having, the requirement is that we must have a particle, mass particle, and we need to show the free body diagram, FBD, as you have learnt in your statics class, the free body diagram of the particle showing all the external forces which are acting on it. Suppose we have, these are your forces, external forces which may be acting on the particle. So these are your external forces which are acting on the mass particle. So as we know, Newton's kinetics states that Newton's second law of motion mathematically states that summation of F bar, if I call it in vectorial format, it looks like that summation F bar must be equal to m times acceleration a bar, correct? So it means that this summation F bar, it is what? This is, in words if you try to express, this is the vector sum of, so we can say this is the vector sum of all external, this is important, all external forces, that you need to take all forces, external forces acting on the particle, acting on the mass particle, acting on the mass particle as disclosed in its, as disclosed by in the free body diagram, in the FBD. So you take the free body diagram, show all the forces which are acting on the particle and consider this thing. And this is equivalent to, this is of course the mass of the particle, mass of particle, and you need to remember this A bar, correct? This represents the absolute acceleration. This is very important. It represents absolute acceleration as measured from an inertial reference system, as measured from an inertial reference system. That means your reference system either needs to be absolutely fixed, taking into consideration nothing in this universe is absolutely fixed. For us, any reference frame mounted on the earth is considered to be an absolutely fixed reference system. So either our reference system is absolutely fixed or it may be moving with a uniform velocity along a straight line, correct? But it should not have any acceleration, neither it should not have any rotational motion or angular velocity. So you need to remember these things. So the acceleration is the absolute acceleration. So what it says that the sum of the combined effect of all these forces essentially is equal to your mass times acceleration. So if this is your center of mass or the particle here, so to say, we can say this is the center of mass, and if this is your acceleration vector, suppose this is my I just arbitrarily show that this is my acceleration vector a bar, correct? So it means that the sum of these forces, the sum of all the forces, say this is F1 bar, this is F bar 2 ... this must be equal to mass times ma bar. So this must be equal to this. So this diagram is called equivalent kinetic diagram. This is called equivalent kinetic diagram. So you have a free body diagram on the left hand side, and on the right hand side you have this equivalent kinetic diagram. Whenever you will be solving this particle kinetics, please draw these figures and start doing the sum. And also, also what we need to remember that this equation, that the motion can be in general, if we say rectilinear is a special case of curvilinear motion, right? Rectilinear motion is a special case of curvilinear motion. So in general, this, the acceleration will be having, say, two components. Either it will be having a bar x, a bar y, or it will be having a bar n, a bar t, or it will be having a bar r, a bar theta. So accordingly, we see that this vector equation, this is a vector equation. So this vector equation, I mean to say this vector equation is ultimately equivalent to, you can write that if you express your acceleration vector as a bar x and a bar y, so you can say summation fx is equal to max and summation fy is equal to may, where you must understand summation fx means sum of all the forces, external forces resolved along some x-axis. Say for example, whenever you need to draw the free body diagram, always you need to show your reference frames. Say for example, this is your reference frame, x and y, correct? So in that case, we see summation fx will be equal to max. That means sum of all the forces along this x direction must be equal to m times x component of acceleration of the particle, and similarly we can write summation fy equal to may, where ay is the y component of acceleration of the particle along the y-axis. Exactly in a similar manner, instead of x and y axis, you can have normal tangent coordinate system. Correct? If this particle moves along a curved path, so you can have a normal tangent coordinate system. So for them, my equation would be then what we see, it is summation ft or normal. So we can write summation fn. Okay, आगे normal टाइप लिखी. Summation fn will be equal to man. An is the normal component of acceleration. Similarly, summation ft, this represents the sum of the forces along the tangential direction. So it is mat. Or if we go to use the r theta coordinate system, I write summation fr equal to mar and summation f theta is equal to ma theta. So if you see here, for plane, this is are all, you can say these are all the scalar equations. We can say these are your scalar equations. Scalar equations of motion. Scalar equations of motion in 2D. Scalar equations of motion in 2D. So in 2 dimensions, I have this scalar equation. So if you take any one row, what you find? You have only 2 scalar equations at your disposal. So it means in case of particle kinetics, the maximum number of unknowns that you can solve, max number of unknowns you can solve is limited to how much? How many? Maximum number of unknowns is 2. So you cannot solve more than 2 unknowns here in this type of problem when you are discussing it's a 2D problem or 2-dimensional or a plane motion problem. However, if it's a space motion, corresponding number of motion unknowns will become equal to 3. But not more than 2 unknowns you will be able to solve. This is the insight of your equations of motion. Okay. And coming back to the rectilinear motion, which is a simple subset of a curvilinear motion, what you will find here is this. Suppose if your particle is constrained to move along the x-axis. Say this is the x-axis and your particle is constrained to move along this dimension. What essentially then means that you have the acceleration only in the x direction. So the acceleration of the particle is lying in the x direction only. It simply shows the ay component or the perpendicular component of this direction of motion is simply 0. So therefore, for rectilinear motion, you see the maximum number of equations is 2. What are they? They are sigma fx equal to max, or we can write it to be equal to m into a, and sigma fy, this is equal to simply 0. This is nothing but equilibrium equation. So this is the equilibrium equation in the y direction. In certain problem, this equation may become a trivial equation. This equation may become a trivial equation. Trivial means it is auto-satisfied. 0 equal to 0 is a trivial relation. 2 is equal to 2 is a trivial relation. So your equation may be trivial, may be trivial. So if it is a trivial one, you do not have to take into account. However, if it is non-trivial one, that means it is not automatically obvious. In that case, please remember you have these two equations at your disposal. So again, you see the max number of unknowns that you are going to solve is of course limited to 2. Now with this, this is the basic, the theory, and of course as you know that in SI system, the unit for the force will be going to be in Newton. Sometimes the units are also expressed in kilonewton form, which is 1000 Newton. And you need to remember the mass is expressed in kg, and g, that is the acceleration due to gravity, unless mentioned otherwise, we will be going to take g as 9.81 meter per second square. If nothing is mentioned, take g as this. Please do not take g equal to 10 meter per second square, what you used to do in your school days. Please do not do that. G is taken to be equal to 9.81 meter per second square unless mentioned otherwise. So with this modest, কিছু বলবেন?
হ্যাঁ স্যার ট্রিভিয়াল রিলেশনটা আরেকবার বলুন।
Trivial relation means কি? Trivial relation মানে হচ্ছে যে here this equation will be automatically obvious, right? You do not have any force in the y direction, so automatically sigma fy will be 0 and 0 equal to 0, correct? So suppose if in your problem you do not have any force acting on the body along the perpendicular direction of motion, correct? In that case, this equation summation fy, since no force is acting along the y-axis, so naturally summation fy is going to be 0. So fy is simply 0, so it means that it is going to be 0. So 0 becomes equal to 0. Now that is quite natural, so that's why it is called a trivial relation. However, if you do not have, if you do have the forces in the y direction, then it may not be naturally obvious that the summation of the force in the y direction in case of rectilinear motion along the x-axis is 0. So in that case, you need to write that equation that it is equal to 0, and from there you may have to solve certain unknowns, and that is basically termed as a non-trivial equation. So when the equation, no force in the y-axis, this equation will become trivial. When forces exist along the y direction, perpendicular direction towards your motion, of course you need to take into account that those forces, sum them and equate them to be equal to 0, because your equation is a non-trivial one. বুঝতে পেরেছো?
হ্যাঁ স্যার।
Okay, thank you. Now if you see here, we go to this the Merriam book once again. And now I come to the kinetics of particles. So let me just magnify this view. This is chapter 3 of your of your book. And very quickly, if I go to this thing, you see here all these things are written. Start with the rectilinear motion 3.4. Previous to that, you have certain articles just for your knowledge sake, you go through them, and all these things I have already mentioned. Please do not bother about your three-dimensional cases, because three-dimensional cases we are not going to deal right now. Now, to start with the problem, let me first take a very simple one. Simple problem. Suppose we are, say, given a problem something like this. Say, we take this problem here very quickly, and I will ask you to, I may not be having the time to solve your problem, so I'll ask you to finish it up at your home, just, discussing this problem here. So let me go to this section and just, take this one. So this is your problem. Okay, I think it is visible to everyone. So it is being given again. This is unfortunately the SI system. Don't worry about the unit. It is being given the 100-pound crate. So if you are to at all solve the SI system problem, in SI system FPS unit, as you know, G value is to be taken as 32.2 feet per second square. So that is the value of G in FPS. Although I assure you there will be no such FPS problems in the exam, neither in the mid semester nor in the end semester there will be any exam, any problem in FPS. If at all there is such problem, we will reconvert them in SI system. However, in the class we may have to solve certain FPS type of problems like this. So here what is said, the 100-pound crate is carefully placed with zero velocity on the inclined plane. So this is an inclined plane, which is a rough inclined plane, where mu s value is being given to be equal to 0.3, mu k value is being given to be equal to 0.25. This is the static coefficient of friction and this is your kinetic coefficient of friction. You have to be very careful when in dynamics problem the static coefficient of friction is being given. It means that your problem may not fall under the statics. For example, describe what happens if theta equal to 15 degree and theta equal to 20 degree. It is my hunch that for the first case, theta equal to 15 degree, there may not be any motion at all. So just we like to see that what is the angle of repose corresponding to this mu s equal to 0.3. So this you know the angle of repose in this case will be what? So you know this we can here, okay. So we just take 0.3, sorry. We just take mu s is equal to 0.3. So we just take 0.3 and inverse of tan, right? Tan inverse, where it is something like this. So you see the angle becomes 16.699 degree. So it means that for theta equal to 15 degree it is, so you see here angle of repose here, that means you know the tan inverse of mu s. So that is in this case is 16 point, how much we get? It is 16.7 degree. Yes, 16.7 degree. So it means as long as your theta is less than this tan inverse of mu s, there will not be any motion because it will be automatically in balance. So for the first case, theta equal to 15 degree, since it is less than 16.7 degree, so for the first case A, there is no acceleration, no motion, all will be simply zero. Because it is, you know, with zero velocity. So it means that there is no acceleration of the block. However, as you see, for theta equal to 20 degree, it exceeds the angle of repose value, the motion will start. So very simple. Now we like to draw the free body diagram of this. I am using this figure itself to draw the figure, to draw the FBD. Please do not copy me. You need to draw separately the free body diagram. So what I am doing here something like this. Please do not follow my approach, right? I am doing it for you know the brevity. I am doing it. For you, you need to draw your proper free body diagram. Otherwise, marks will be heavily deducted if you try to solve the problems without drawing the FBD, proper FBD. So you see this, I take it as the x-axis. This is a rectilinear motion problem, y-axis, because the motion of this crate is along the straight line. So this is how you need to do. Now you show your free body diagrams. We see you have the self weight, and the self weight, since it is placed on the inclined plane, can be divided into two components, one perpendicular to it, which will be 100 cos 20 degree. This will be one component, and the other component will be 100 along the x-axis. This is 100 sine 20 degree, so much of this thing. And you have the normal reaction. Assume this to be a particle. You have the normal reaction here, capital N. Since it tries to fall, it moves in motion in down the plane, correct? So there will be a friction and the friction force will act in the upward direction. Since there is a motion, so for block B, block will move, block moves, and in this case it will be your kinetic friction force. So we say this is Fk, and that is being given by mu k into n. So this is the thing equivalent to, now this is the free body diagram, which I have shown. This is being equivalent to, you see, if I consider this block here like this, it is moving with this acceleration. So only it is having acceleration in the x direction. Y direction, it does not have any acceleration, but in the y direction you do have forces. So it means summation Fy equal to 0 is not a trivial equation. It is now a non-trivial equation. So I say this is equal to 100 by 32.2 is the mass, correct, multiplied by the acceleration of the block. I say it is A. So therefore, my equations here will be summation Fx is equal to max, right, and summation Fay and summation Fy is going to be equal to is going to be equal to 0. It's going to be equal to 0 here, correct? So I attack this equation first. From this I can write, from this equation I can say obviously that n minus 100 cos 20 degree, this is going to be equal to 0, or in other words we see that n becomes equal to 100 cos 20 degree. So this is done. Now summation Fx equal to max, so it simply means that 100, now from the second equation we can write it is 100 sine 20 degree minus the mu k into n, mu k is 0.25, so it is 0.25 into n we have solved, which is equal to, you know, the 100 cos 20 degree. 100 cos 20 degree, this must be equal to 100 by 32.2 into the acceleration of block A. So I see therefore that acceleration of block A will be ultimately 32.2 into sine 20 degree minus it is 0.25 into cos 20 degree. So that so much of feet per second square will be the acceleration, and that too will be in the down the plane. So this is a very simple problem, and intentionally I select this simple problem at the beginning to just explain you how we can apply our equations of motion. That someone is asking me that why it is in what is meant by a trivial equation. So you see, this is not a trivial equation, because you do have forces in the direction of motion, and then you need to announce that, okay, since the predominantly you see that the motion of this block is down the plane, so you need to announce to the community that, okay, I don't have any motion along the perpendicular direction. In other words, it means that your sum of all the forces which are acting along this perpendicular direction, they must be 0, or they must be in equilibrium. That means this block must be in equilibrium along the y direction. However, it is not in equilibrium in the x direction when your theta becomes equal to 20 degree. So dear students, we stop here today in this segment, in this class. And you know, when we will be meeting again next day, we will be talking about the you know, the further discussion will be done on particle kinetics, and no theory, all will be, you know, the problem based thing, because we have almost completed the theory of particle kinetics in this case. So no new theory will be given to you until unless we move to the next module of kinetics, that is the work energy and other aspects, and momentum, linear momentum, impulse momentum aspects. So at this point we stop here. our class recording and we see, sorry,